Okay, now my clock says that it's 7 o'clock here where I'm sitting in the world. And welcome to this session called Programming Languages Free. And we have a couple of really exciting presentations lined up here, 5 minutes each. And while we run them after each other, and then as you listen to the talks, please write questions in the chat. And then we'll pick them up afterwards and have a joint discussion. So now to kick us off, we have Michael Schroeder who will talk about grammars. Please go ahead.
Yes. All right. Let me just share my screen here. Okay, can everybody see my screen? Great. All right. Hi, everyone. My name is Michael Schroeder. I'm a PhD student at TU Wien in Vienna, Austria, where my PhD advisor is Jürgen Zito. And this is Grammars for Free, our vision toward grammar inference for ad hoc parsers. So you probably have written code like this before. This is a simple Python expression that turns a string of comma-separated numbers into a list of integers using just some standard functions like split and map and the Python int constructor. This is what we call an ad hoc parser. It doesn't use any particular parsing techniques or parsing frameworks, but it's clearly parsing a string according to some kind of implicit grammar. These kinds of parsers are everywhere. Anytime that you do anything with a string, whether you split it or you slice it or you just trim some white space, you're in fact parsing the string. You're imposing some kind of structure on the string according to some kind of grammar. And while you most definitely have written an ad hoc parser yourself at some point, you may not have written down a formal grammar for your ad hoc parser. In fact, I'm pretty sure you haven't probably. So at least not for these kinds of small examples. Here are two equivalent grammar representations for our little example. And these are finite but complete formal descriptions of all the accepted inputs of the parser. So basically all the values that this string S can have without the program going wrong in some way, right? And there is an analogy here with types. Just like types, grammars are a formal specification. So a parser without an explicit grammar is very much like a function without a type signature. So it's probably still going to work, but maybe not in the way that you expected. And if you don't have the type signature or the grammar, you won't have any guarantees about it before you actually run the program. Whereas if you had the type or the grammar, you could reason about the program's behavior. So types have one significant advantage over grammars. Most type systems offer some form of type inference, allowing programmers to generally omit type annotations because they can usually be automatically recovered from the surrounding context. Now, what if that was possible to also do for grammars? What if we could infer grammars just like we can infer types? And this is exactly what we want to do in our work. So here's an overview of our end-to-end grammar inference system as we envision it. Now, obviously, I don't have time in this short presentation to go into all the details, but so the basic high-level idea is that we take some ad hoc parser source code written in a general purpose programming language like Python. We carefully simplify it into an intermediate representation, which is basically a domain parsing. And then from this intermediate representation, we infer a language model, very similar to how one would infer types. And in fact, we're using some of the same techniques. And then from this abstract language model, we can generate grammars in various textual or visual forms. So all of this is still, a lot of parts of this is still, at least still a work in progress. But if we have this automatic grammar inference system, then it enables a whole range of new applications that haven't really been possible before. So first off, with inferred grammars, we could use we could use them as some kind of interactive documentation. So that is documentation that is always up to date and that is closely linked to the underlying source code. So imagine, for example, as in these mockups, an IDE plugin that shows you the implicit input grammar for some function when you hover over the function definition, and that maybe lets you drill down into individual production rules or non-terminals of the grammar and trace them back to their origins in the source code. Or another new possibility would be bidirectional parser synthesis. So when you combine this novel grammar inference with existing parser generation techniques, then you can do semantic program transformation. So for example, what you could do is you could do a grammar-based program sketching as illustrated here. So you start out with an incomplete program, a sketch, and then use grammar inference to get some initial grammar that the user can then manipulate and refine just on the level of the grammar. And then the refined grammar can then be synthesized into a refined program. And finally, we also envision some interesting applications in code mining and learning. So because a grammar is basically an equivalence class over concrete implementations, it allows us to group together different parser implementations with similar semantics. So we can use this to build grammar-based code search, where the user could query for certain production rules or grammar patterns, and the search engine returns specific instances of implementations of these grammar rules. Or if we add a history component, we can watch how grammars change over time, enabling some kind of semantic change tracking. So you could imagine a build bot, for example, that augments the code review process with current and historical grammar information, so that the programmer is alerted when a code change introduces a change in the input grammar. And we are hoping to realize an end-to-end grammar inference system and some of the applications I've just described, at least in prototypical form. And to this end, we're working on a number of related projects where you can find more information about these in the paper and the long-form video. And the paper and the video also have more background and our intuitions behind how and why we think this inference process is actually possible. But for now, I want to thank you very much for listening to this short presentation. And I'm really excited about the possibilities of this automated grammar inference. And I want to invite the community to collaborate with us to realize this vision of grammars for free.
Okay, thank you, Michael. Remember to write questions in the chat as they sort of appear, and we'll pick them up later. Now we'll switch over with this rapid program that we have to Dominic Seifert, who will talk about the synchronous call graphs. Please go ahead.
All righty. Okay, is this all good? Can you see everything? Hello, can you hear me?
Yes, all good.
Okay, good. All right. Okay, I'm just going to get started. Okay, thank you very much. I've been working, or rather, we have been working on an asynchronous call graph for JavaScript. Let's see here. How do we do this? Perfect. The goals are pretty simple. We want to capture all of asynchronous control flow as a network of virtual threads, and ultimately be able to visualize them and make them interactive. So this is not automatic debugging, but this is rather focusing on making it useful to the developer and to show the developer, and not only to show it, but also make it just nice and interactive. So basically, whatever you can see, you can click. That's kind of like the sort of guiding principle here. In general, we are very passionate about interactive debugging, and we believe that there has not been done enough, especially in terms of program comprehension and finding the bugs in our applications. There's just not really good, mature tools, and they haven't really evolved in 55-something years. All right, now, let's look at an example. I love this example. I've come up with a random piece of code, and I was like, yeah, this is a pretty good graph. So this is what I like to kind of like show for the first time, every time. Here we see a piece of JavaScript code, assuming you can read code. We see that F1 is followed by, okay, kitty cat, all right. F1 is followed by sleep for 1 second, and then by F2. And there's basically a very clear serial relationship between these three pieces of code. And we can see that the ACG, the asynchronous call graph, automatically extracted all of that here on the right, and put it on one column. On one of these columns, we call them a virtual thread, because it's very much like a traditional kind of thread. And then at the same time, basically concurrently, we have this other thing going on. G1 followed by G2, and then H1 followed by H2. And basically, this is the actual execution timeline, where the time goes from top to bottom. And another thing that we can see here is that we can also support async functions. I think, especially in JavaScript research, kind of like the trace loggers, they've kind of like stopped evolving. I think very few of them actually support async functions. So that's a little bit to brag about. But ultimately, it just grabs everything that's asynchronous. So it does, we'll look into that in a second. It has these awaits over here, and even can make sense of this promise.all over here. And also, like, the entry point was cut off, it's over here, but basically we can also see it's being forked from the entry point over there. All right, now background, I'm going to skip all that. Just realized I totally over-prepared. And also definition, well, that might be good. ACG is a DAG, and the nodes are basically these atomic pieces of code that will run because they are dequeued from the JavaScript event queue, or rather any of the event queues, really. And they will ultimately, well, they will start when they are dequeued, and they will then run to completion without interruption because of the non-preemptive property of JavaScript. And all of these things, these pieces of code that run uninterruptedly, we call them call graph roots. And these are the nodes of our ACG. There is at the core the at-edges algorithm. Probably not going to go into detail on that, but note that basically the most difficult aspect is, okay, we see a new CGR. We just recorded a new piece of code that was dequeued from the JavaScript event queue. By the way, we're using user space. This is like, we're not touching Node, we're not touching a browser, we're not touching V8. All of that is in user space using instrumentation and a runtime library. And so we recorded it. We send it back to our backend. And in real time, you can then see all of that happening there. Then the biggest issue here is that here, look for possible chains. That's the biggest problem. And that relates to the two types of rule sets that I have also mentioned in the other video. Now, that doesn't matter much because I don't think a lot of people saw that video, so it's fine. Either way, if you ever see it or if you read the paper, these are the two types of rule sets we're talking about. If you can, okay, let me actually skip that as well. Okay, I love this, for example, because this was like kind of like my original motivation. We have this piece of code. Sorry, we have a function f. We have this piece of code, and this is the ACG as a result of it. If we look at this here, we see this little g over there. This is kind of like tricky because the first time you see this, you might not pay attention to g, but g is one of the most important things of this piece of code, or these two pieces of code fused together. You might also not know that this is the exact order of events. You will have A followed by F, followed by B, followed by C. This is not obvious that easy to read, but ultimately you fork off G twice because we are not awaiting it. Now, if we actually awaited this thing, we would actually have a serial flow of events. And again, the ACG can grab all of this automatically. And these Gs, there's no potential for race conditions here while there is here. And this is, of course, one of the many potential applications to see obvious race conditions or obvious potential for race conditions. All right. Oh, wait, I'm over time. Oh, well, that's too bad. Should I give it back to you, Emma?
Okay.
Here's a quick example. Here's another quick example. Sorry, with key event handlers. This is a front-end application. We have all kinds of cool things. Anyway, thanks for listening. Here's some links, all that. Thank you.
Thank you, Dominic. We'll get back to this in the discussion. Very interesting. But we'll jump over now to try to stick to our schedule. Now, Xu Fei, please tell us more about learning and programming challenges of Rust, and then you can take over the screen share. Thank you. And remember to post questions in the chat. Please indicate which presentation that you're referring to if you can as well.
Yeah. Hi, can you see my screen?
Yeah.
Looks good.
Great. Hello, everyone. I'm Shufei Zhu. I will present my paper, Learning and Programming Challenges of Rust, a Mixed Method Study. This is a joint work with authors from Penn State, Wisconsin, and China Telecom Cloud Computing. Rust is a young programming language designed to provide both low-level efficiency and high-level memory safety and thread safety. Rust conducts strict compiler checks to achieve this purpose. Rust's popularity is increasing dramatically these years. According to Stack Overflow surveys, Rust has been the most loved programming language since 2016. Rust has already been adopted to build many safety-critical software systems, such as OSs, browsers, and blockchain systems. Rust's safety mechanism centers around two important concepts: ownership and lifetime. The basic rule only allows value to have one and only one owner. Value is dropped when the owner's lifetime ends. To improve the flexibility of coding in Rust, Rust extends its basic rule to multiple extended rules. For example, Rust allows to temporarily borrow a variable's ownership using a reference. A reference can be immutable for read-only accesses or mutable for read and write accesses. Rust allows multiple immutable references to a variable to exist at the same time, but it only permits at most one mutable reference to a variable at any time. All these rules are checked statically during compilation. They essentially prohibit having mutability and aliasing at the same time. They together can prevent many severe memory bugs and concurrency bugs. Unfortunately, Rust is known to have a steep learning curve as it's difficult to program in practice for two reasons. First, Rust's safety mechanism is very unique. It is very difficult for programmers to migrate their previous programming experience. Second, The design philosophy of Rust is reject all suspicious code, and Rust safety checks are strict, sometimes overly so, making Rust code hard to be compiled. Let's take a look at a real-world example where Rust safety rules confuse programmers. Variable out1 and out2 are similar to each other, since both of them contain two full objects. However, out1 is an array, but out2 is a tuple. Function test takes two full objects as inputs. It uses a mutable reference to borrow the first full object and an immutable reference to borrow the second one. Function test is called here using the two full objects in the array as inputs, but the Rust compiler reports an error on this line. The reason that the elements of an array must be borrowed altogether in Rust, since the Rust compiler conservatively assumes an index can access any element in an array. Out1 has already been mutually borrowed at the first parameter. Thus, it cannot be borrowed again at the second parameter. The second function call uses the two full objects in the tuple as inputs. Surprisingly, this call is allowed by the Rust compiler because different tuple fields are borrowed separately in Rust. This example demonstrates the complexity of applying Rust safety rules. Besides the safety rule that a mutable reference cannot coexist with another reference to the same object, programmers must also know how array and tuple elements are borrowed. Without a clear understanding of these, it is very easy for programmers to make similar mistakes and write programs rejected by the Rust compiler. To systematically understand the programming difficulties of Rust, we conduct an empirical study on Rust-related Stack Overflow questions. We focus on questions related to safety rule violations. To conduct the study, we first build a taxonomy for the root violations. We then apply two statistical models to pinpoint when a safety rule is more confusing. Finally, we inspect whether the Rust compiler provides all necessary information for programmers to comprehend the violations. We got 6 findings from the empirical study. To validate the findings of the empirical study, we conduct an online survey on Qualtrics. Besides directly asking participants for their previous experience in coding Rust, we also show them small programs containing safety rule violations and design questions to observe how participants comprehend the violations. In total, we received 101 body responses from real-world Rust programmers. We conduct extensive data analysis on the response to check whether they are consistent with the findings in the empirical study. We observe that Rust safety rules are difficult to apply in concrete coding scenarios. Sometimes, error messages provided by the Rust compiler may not be helpful enough. In total, we gain 6 findings about the programming challenges caused by the Rust safety rules. Those findings can be useful for Rust learners and programmers. Moreover, the findings are confirmed by the online survey with statistical confidence. So here's all of the findings in the empirical study and how they validated in the online survey. Feel free to give questions.
Okay, thank you. We'll take questions after all the presentations, but please write them in the chat, and thank you so much for your presentation. Now we'll jump over to Sing, and please go ahead.
Can you see my screen? Hello, everyone. I'm Xing Zhang, a 2-year PhD at Peking University in China. The title of our work is Towards Bidirectional Live Programming for Incomplete Programs. This is a joint work with also from Peking University. To combine the intuitiveness of direct manipulation on the output with the abstractness and repeatability of text-based programming, researchers have developed many useful bidirectional live programming systems, which can not only allow developers to see continuous feedback by evaluating programs, but also allow them to directly manipulate the output to automatically synchronize the program. However, there is a big limitation. They cannot deal with incomplete programs where code blanks exist in the source programs. In practice, developers tend to program in a way where they skip some parts by leaving some code blanks during programming. It would be practically useful if, even when the program is incomplete, developers could still directly manipulate the output and automatically synchronize the program. Fortunately, Omer has made a nice progress in unidirectional live programming for incomplete programs. They model incomplete programs as expressions with holes, which denote missing expressions. They track the evaluation state, called closures, that is, variables with their bindings that can be accessed by hosts. With the technique of live programming for incomplete programs, what we need to do is to make this technique bidirectional to achieve the goal of bidirectional live programming for incomplete programs. Let me show you an example. F is a function which concatenates X with a hole represented by a red question mark. The final expression is a tuple where the two elements are function calls that applies F to ICSI and 2021, respectively. The output is a tuple of two hosts named star1 and star2, which are equipped with hole closures. For example, ICSI is bound to the variable X in the closure of hole star1. Both the output values and the hole closures allow modifications. For example, we change the binding of X from 2021 to 2022. Then the program updates correspondingly. On the other hand, if we change the two hosts to two determinate strings, our system will generate requirements that hosts must meet. Therefore, two requirements are added to the hole bindings table, which describe the output values of evaluating the hole when X is ICSI or 2022. Interestingly, we run the program with hole bindings again to get the output that is exactly the tuple that we previously changed the incomplete tuple to. This means that our system satisfies the round-tripping properties. Here is our tool called bidirectional preview. The input is the code written in the editor using our language, and the hole bindings. The output includes the HTML output and the hole closures. The eval button performs forward evaluation, while the uneval and update button performs backward evaluation. Consider the task to implement an HTML table to record the birthdays of classmates as follows. Developers can implement the logical framework first and set the details to hosts. For example, the spacer and the color variables in the program are set to hosts. Evaluate this incomplete program. The incomplete prototype is shown on the right, where the second column is missing and the first and third rows have no color. We can edit content. For example, we change the hole star2 to a string. Then we get the requirement for the first hole. We can also edit colors. For example, we change the color of September 5th to light yellow. Then we get the requirement for the second hole. Evaluate this incomplete program with two hole bindings. We can obtain a complete output that we desired. To sum up, we propose the first framework to support bidirectional live programming for incomplete programs. In particular, we carefully formalize a bidirectional evaluation for incomplete programs, which satisfies round-tripping properties. For theoretical details, welcome to read our paper. We also give an efficient implementation as a concrete tool called bidirectional preview. The code and more examples can be accessed through this URL. Welcome to use our tool. Thank you. That's all.
Thank you. And questions in the chat, please. And now we'll jump over to Stefan Hannenberg, who will talk to us about collection processing. Please go ahead.
Your mic is not on, I believe.
Thank you.
I'm sorry. Okay.
That's good.
It has a long title, and I make it a little bit shorter. What do we really speak about? The paper is just about two different ways of handling collections, and the traditional way of handling collections is to have an explicit loop and to have certain invariants that you define. And for example, if you take a look at this code here, we iterate over a person collection, and we collect everyone whose age is larger than 21, and then we add it to a result collection, which finally will be processed or returned or whatsoever. And what we have with the Stream API in Java is we have a more declarative way of handling the same code. And it typically means, on the one hand, that we have this stream transformation, which is not that relevant, but the essential thing is here that we have Lambda expressions that are somehow passed to streams in order to determine then the final results. We have a final step, which is, from my perspective, also not that relevant. So the question here is, we have two ways of handling collections. The one is the traditional way with loops, and the other one is the more modern way of having Lambda expressions. And the simple question is, should we prefer one over the other? One could say, okay, Lambdas are more modern, but are they more useful? Why do we think the question is actually relevant? Well, taking a look into the related work, you find a study from ICSE 2016, which actually says that people have troubles writing code that contains Lambda expressions. So it's not really natural from our perspective to have Lambdas in the code, and it's not that natural to say that the resulting code will be better or more understandable or something like that. Okay, so we run a randomized control trial on that. Just to give you an idea, we give two different code representations to our developers, and we just ask them, what is the result of the code? Well, let's take a look at the app that we used. So they have a certain code snippet in the middle, and it's just a function definition. Inside this function definition, we do something on a collection. On the left-hand side, you see the input. On the right-hand side, you see what people can select as output, and they have to choose from the list what the output of this method will be. And then they have to confirm what they've chosen, and then they, I'm sorry, this one is German, just because the application was written in German. They ask three different questions. The first one is, how good do you think you were in this task? How fast do you think you were? And how appropriate do you think the code actually was to represent the function that it is intended to represent? So experimental layout, what did we do? We measured response times and the correctness, and we measured the subjective perception of people. The independent variables were the technique, and we gave 7 different tasks to our developers. And let's just check what we did it on 20 volunteers, and maybe the details, how exactly we ran the experiment, you can get from the paper. The results were actually that in each individual task, the people required longer for loops, which were a little bit astonishing from our perspective, because from our perspective, the loops are the traditional way of writing the code, and from our perspective, also what is typically taught at universities and at courses. Actually, it turned out that it was for our students as well as for the professionals the same situation. So in both cases, people required longer using loops. Spoken in terms of statistics, on average, they required about 80% more time to answer the questions, and they were more often incorrect answering the questions. The next thing is, and I don't give you any details here, they were able to perceive that they were faster with the streaming API, so they considered the streaming API as more appropriate than the traditional loops. So what does it actually mean? Well, it seems like at least loops could be helpful, although we know from the related work that lambdas might have their problems, but maybe not from the readability perspective. So thank you very much. I'm 20 seconds over. I hope you accept my apologies.
That's okay. Thank you so much, Stefan. Okay, then we have our last presentation, Michael Koblenz, who will talk about garbage collection and Rust. Yes, go for it.
Am I coming through okay? My audio working? Yes, okay, good. Okay, thanks. So we already learned a little bit about Rust, so I'll spare you a lot of details about Rust. The short version is that, C and C++, as you know, allow dereferencing arbitrary pointers. And this can be really dangerous, right? So in Chromium, for example, a large fraction of the severe security bugs were due to memory safety problems caused by, code written in languages that are unsafe. So great, maybe we should just be using a programming language like Rust that's memory safe, and then we won't have all these problems. Rust, as you just heard, uses this ownership mechanism to provide memory safety and at the same time avoid the performance cost of garbage collection. A prior study that motivated the work that we did showed that a lot of people feel that Rust is harder to learn than other languages. And a lot of the interviewees in the study felt like the biggest challenges were ownership and borrowing. So we wanted to do something to try to mitigate the usability and learnability challenges of ownership and borrowing in Rust. And so our idea was to mitigate this usability cost of ownership by adding a garbage collector. And the rationale is that, most code is not actually performance critical, right? So the engineering approach that we're proposing is that typically software engineers should use the garbage collector for most code. And then when they discover performance problems, they can switch those particular hotspots over to using ownership, right? So, so we can adopt ownership gradually rather than having to buy in entirely. So garbage collectors work by tracing the heap to find live objects starting from roots. So what we did in our prototype is we modified the Rust compiler to emit LLVM stack maps. And this enables the prototype's runtime to find these roots automatically for cases that are implemented in the prototype. So good, so then the question is, does it actually help people? And so we did a randomized controlled trial with 333 participants in a programming languages class. We gave them 4 lectures on Rust, we gave them 2 live coding demos, and then after each task we gave them a survey to learn about what their experience was like. So here's the structure. First, everybody did this kind of basics task that introduced them to the basic syntax of Rust. So there was no garbage collector here for anybody, everybody just did the simple task. And then afterward, there were 2 tasks, one pertaining to ownership and lifetimes, one pertaining to aliased and mutable data. I'm sorry, somebody's mowing the lawn. I'll just close the door. Okay, hopefully it's better. Okay, sorry about that. So, so we have 2 different conditions. There's the traditional condition and the bronze condition. And you can see that people first did this ownership task, which focused on kind of the basic principles of ownership and lifetimes. Then the aliasing task was trickier. So people who didn't use the garbage collector needed to understand what's called interior mutability, which is a way of managing multiple references to mutable data in Rust, even though traditionally that wouldn't be allowed. So you can see those 2 tasks, ownership and aliasing, had 2 versions. One with an API that was traditional, and one whose API was adapted to garbage collection. And then afterward, people who used bronze needed to redo that last task without the garbage collector. This is so that the learning outcomes were similar in both cases, at least regarding Rust. So let's look at the results. In terms of completion rate, there was no significant difference in completion rates of the ownership task. But the bronze users were more than twice as likely to score 100% on the aliasing task. So it seems to be very, very effective there. That's interesting. If you look at completion time, these are self-reported times. The bronze users finished the aliasing task significantly faster by about a factor of 3, 4 hours versus 12 hours. And you can also see the standard deviation is very large for people who didn't have access to the garbage collector. Some people spent up to about 70 hours. So that was kind of interesting as well. We asked them to what extent they agreed, this is only the participants who used garbage collection, with the statement, garbage collection in Rust makes writing programs easier. And you can see participants were more likely to think garbage collection was helpful after doing the sign-up than before it. But here's what's kind of interesting. So if you look at the yellow and green bars representing agreement, initially about a third of people thought it would be helpful before using the garbage collector at all. And then after doing the challenging aliasing task, more than 3/4 of people felt it was helpful. But what really convinced them to look at the difference in the yellow bars is when we took the garbage collector away and they really wanted it back. When they had to redo the task without garbage collection, then they were really convinced. We asked them how much they liked Rust. Interestingly, there was no significant difference between conditions. So maybe this means that even if you save people time, this doesn't actually mean that they like the language any better. So we were interested in what we could do to make people like the language better. And so we looked at correlations between how much they liked Rust and other factors, like how they felt about how much time they spent compared to how much time they expected to spend, their levels of challenge and frustration that they experienced, and levels of stress. And you can see there's a stronger correlation between how much they liked Rust and how much stress they were under, and how much they liked Rust and how they felt about how much time they spent. So maybe in the future, we should focus on reducing stress rather than reducing how much time spent. We asked them what was most difficult. Was it things like coding with ownership rules and trying to implement immutability was just such a headache? It's like someone who combines the worst parts of C and Java. And you can see interior immutability requires that from the API, either you have to manage reference containers or you use dynamic borrowing. Whereas if you're using garbage collection, it just sort of works. In terms of next steps, we're interested in studying how we can make Rust easier to use. So we did a preliminary study in a Rust course. One observation is that the low-level error messages that insert ampersand right here don't really teach the high-level concepts. So we really need to kind of rethink how to do error messages right. Also, fixing errors that compilers give is a lot like debugging, because you have to understand how the compiler works. But in many cases, we don't really teach debugging very research also. In conclusion, garbage collection significantly reduces the architectural burden of ownership in Rust and can enable completion of complex tasks in less time and less time. So thank you very much for listening.
Thank you.
Thank you.
The sound was breaking up a little bit for me. I don't know if it's only me. Okay. Well, let's see. Okay. Well, hopefully that doesn't affect our discussion. So thank you all the speakers. Very interesting. And now we have this second half of this session to focus on questions and discussions around those. So let's see. I'll start to have a look at what's in the chat. And I think you can probably jump in and unmute and also ask a question if you want. So let's see what we have first. I saw there was one question for the first paper, Michael Schroeder. And this is from Michael Koblenz. Do you want to unmute and try to address the question directly, Mike?
Yeah, hopefully my audio works okay.
Or maybe not. I'll try to repeat it for you. It's not very good for me.
Yeah, there's some feedback.
Something like yeah. Okay, but this is in the chat, so you can see Michael Schroeder. So I'll repeat it. It seems like the inference will quickly get into undecidable problems, right? Since the ad hoc parser can be arbitrarily code.
Yes. Yeah, that's a great question. So we go into this a little bit in the paper and in the longer video. Of course, if we try to analyze some code in a Turing complete language, there are these like limits. But the intuition is that most probably this ad hoc parser code, or any kind of parser code really, structurally will follow more or less the language that it parses, right? So a parser that parses a context-free language will itself usually not be much more powerful than context-free, like looking at the code structure, right? So basically this is kind of a more specific kind of story here than just a general. If you want to use formal methods on code, in general we can do much, but of course the kinds of programs that are actually written are usually amenable to at least some analysis. And so in the same way, the analogy here is that if you write a parser and the parser happens to parse a language that's regular, then probably the parser itself is not much more complex than regular in its structure. Of course, there might be exceptions and border cases, but we think for most practical applications this will be true.
But even if it's true, you could write the code in such a way that can be very hard for the inference system to figure it out.
Yes. I mean, you could, of course, in kind of an adversarial programmer could try to write a parser that is, ridiculously complicated to do stuff that is kind of unexpected. But I mean, also from what we've seen from like the kinds of parsers that are in the wild, these kind of ad hoc parsers, I mean, they usually don't do it. But I mean, undoubtedly, there would be some cases where that might be the case, and then it would be undecidable, right? But it's kind of like a best effort kind of thing, and I think that would already get us a lot of the way there.
Okay, thanks.
I had one. Any other questions in relation to the first paper? I had one just, interested if you thought about taking it further beyond syntax towards semantic specification and so on. Is that something you think is possible, or have you even thought about it?
Do you mean? Semantics
well, I mean, thinking about specification of compilers, you have some formalisms for doing that, and so on. Could you, infer some semantic specification as well?
You mean not just infer like syntactical grammars, but like other kinds of semantics? I mean, basically, I mean, I guess the way we want to tackle this inference is via a refinement type system that's kind of extended and modified, and that kind of in the process we're generating all these verification conditions, basically invariants over the program that can be interpreted in some ways, under some models with certain semantics, I guess, if you choose, certain domains. I mean, we are choosing to interpret it like in this kind of limited grammar way. That's kind of what we're interested in finding out. But depending on, I guess, the precise approach that we end up using, it might be that we could modify this to like have some other domain of semantics that we could maybe infer, I guess.
Okay, thank you. Okay, let me see if there's any other question that popped in. Otherwise, I'll...
May I also ask a question for the first paper?
Oh, please, go ahead.
Just from the usability perspective, because so the way how the paper is written is I write my code first, then I infer the grammar. And the traditional compiler guys do it the other way around. Like they write a grammar and then they compile the code. In your and typically they don't care about that much about the code. I mean, they test it, but they never try to debug it or whatsoever. In your case, you have now two representations of the same concept. What do you think will be the artifact that you will finally work on most?
I mean, I think that depends a lot on the context of the domain of the exact problem, right? So yes, I mean, a compiler programmer, right? He will care about he will have a huge grammar, and he maybe doesn't care so much about the parse implementation, except maybe as far as performance or something goes, right? But of course, in this kind of case of these little ad hoc parsers, right? If you have some business logic, and in there somewhere you're parsing something in between, right? You might care. It's a much smaller thing, and there you really might have kind of the code first, right? And maybe the grammar more as a documentation thing. But then on the other hand, maybe if it's like a problem that you're trying to solve, where you want to parse some document or something, or some file format, and you're not quite sure, and you'd rather get started writing code, then you can do this like what you explained, this bidirectional synthesis thing, where maybe you start with writing code, and then you can see, oh, actually this code I've written, the grammar that it parses is not quite what I want. There are some edge cases that I haven't thought of, and then you may modify it on the grammar level, right? So I think it really would depend on the type of user using it, and we don't really envision, I think, this being so much used by kind of compiler programmers, people who write really big, huge parsers, but more like everyday quote-unquote software engineering, where you write all these ad hoc parsers all the time without really thinking about the grammar. And this gives you a way to actually think about the grammar, a way that's more accessible than sitting down and thinking of a specification, right? It's more like a type inference in that way, right? Rather than like a big thing. It's more like, it's supposed to be like a lightweight kind of thing. That's the idea, at least.
Okay. Thank you.
Thank you. I also wanted to draw. Maybe we can get back to it, but let's see if we have some other. Just see if there are other questions also for the other papers. So I was, especially since we have 2 papers covering Rust, it seems like you have some connections there. So I'm kind of curious of your thoughts here, Xiufei and Michael. Now, when you have your mic fixed. So Xiufei, you listed a number of challenges there in the paper about Rust, and then we have Michael and their work looking at some of those challenges. Do you have any comments on the other papers?
Sorry. I would just tune in my microphone. So, can you repeat the question again? I'm sorry.
What do you think about? So in Michael Copland's last presentation there on adding GC to Rust, it's a way to sort of address some of the challenges that you list in your presentation, right? About ownership and so on. I was just curious if you two had any kind of reaction on each other's work, given that you're kind of in the same space.
My understanding is my understanding our work focuses on the challenges that programmers already met in using Rust. I think some of the challenges can be solved by a garbage collector. But I think, as also mentioned in Michael's paper, some of their participants still need to understand the basic concepts of ownership to have eventually in their experiment. So I think adding a garbage collector can help Rust programmers learning more about can help Rust programmers making their experience easier. But I guess programmers may still need to learn some of the basic concepts. That's my understanding.
So I have some follow-up work that isn't written up yet that kind of relates to Xiufei's work. So I also did a study looking at Stack Overflow. We looked at I don't remember exactly, I haven't written it up yet, but something like 1,000 of the top Stack Overflow questions. And, you know, like I mentioned in the talk, we also did a study in the context of a course, you know, observing students and watching them, you know, struggle with the homework. And so, you know, I saw kind of a broader range of problems in those 2 contexts. So, you know, I think it's hard to pin down the problems on 1 or 2 particular things. You know, it is a complex type system. And also it's, you know, it's a programming language. And when you study novices, you're going to get people who are confused about programming things. And some of the people who post on Stack Overflow are novices and some of them are not, right? So it's kind of hard to tease all those things apart. You know, a lot of people are confused about the standard library. You know, and the design of the standard library relates closely to the design of the language, but it's also its own artifact. You know, so I think we need to sort of take a nuanced look at all of the different aspects.
You have any other thoughts on how to intervene here? You have been exploring adding a GC. Other potential things that could be done in terms of adding tools or something like that?
Yeah, so, you know, one thing that I think is really that, you know, to really understand why the compiler is giving you an error message that it's giving you, you are forced in Rust to have to understand the compiler to some extent, right? Obviously not the entire thing, but, you know, if you want to understand why the borrow checker is complaining about something, and, you know, this is true in general for safe languages, right? They're conservative and they will complain about things that are actually safe. And so you have to understand why it is that the analysis results in the error that it does. And so I think, you know, choosing analyses that are simple and then providing mechanisms to let the compiler explain itself if you look at the Clang static analyzer, when it gives you error messages of various kinds, it'll actually draw diagrams in Xcode. Why is it that this variable your reference can be null? Well, first you have this assignment, and then you enter the body of this if statement, and then you go around this loop 3 times, and then here's where it's null. As opposed to if you just tell the programmer it might be null, it's like, well, it doesn't look null to me, right? So I think these kinds of tools can be really helpful. This RustViz project by Cyrus Omar and his group is kind of interesting in that it's supposed to be a teaching tool. So it basically provides an instructor way of generating nice diagrams that visualize transitions of ownership and lifetimes. So I think that's interesting. But the tool that the RustViz specifically is an instructional tool. It's not primarily a tool for users. So I think it'll be important to sort of think about how we take that tool and put it in the hands of regular users. Stefan, you had a question. How much of the study is Rust and how much of it is garbage collection? Could a comparable experiment be used to test what the overall effect of garbage collection is? Yeah, that's a good question. What I really think the study showed is the architectural impact of garbage collection in Rust is very large. And if you're not using garbage collection and you're using instead interior immutability, because that's what Rust forces you to do, if the design of your objects are such that you need multiple aliases to mutable data, interior immutability is tricky for novices. You have to understand the temporary objects that you get when you borrow something temporarily. You have to understand what it means to move these checks from compile time to runtime and what those checks are and in what cases they run. And it's subtle, right? So whether code is safe dynamically depends on whether the 2 borrows that you have coexist, right? And whether they coexist depends on how long each one lives. So you have to really understand the Rust lifetime semantics and when things are dropped in order to use that correctly. So you could say that this wasn't really about garbage collection; it was about architecture. But the architecture is a result of the type system that Rust has and the implications of its restrictions. And garbage collection is one way of getting out of it, right? So then you might ask, well, okay, what are the implications of the study on the question of Java versus C? And I think the answer is, well, the implications are not very strong because the architectural implications are very different. So, I think we probably need a different study to understand garbage collection in the context of Java versus, C manual memory allocation. So the overall effect of garbage collection, I think there are lots of implications there. Likewise, you could ask, let's say you don't really care about leaks, right? Let's say you're primarily interested in safety. It's maybe not as hard to get a C program right if you're not worried about leaks. You just never free anything, right? So then you say, well, now I do care about leaks. Why do I care about leaks? Because I care about performance. Oh, if you care about performance, then maybe you care about how much time you're spending freeing objects, right? And so then you could do a study, okay, for a given amount of performance, how much extra time do you have to spend if you have a garbage collector that you have to work around? I think there's another interesting effect, which is, I talked to some people who said basically, look, I used to program in Java, and then I needed more performance than the garbage collector could provide. And then I got very frustrated, and I had to throw out my whole code base and rewrite the thing in, well, in this case, Rust, because Rust is not garbage collected, right? So if you've been burned by that and you've had to rewrite your entire code base, for this reason, you might never use a garbage collected language again, right? If you are, right? Because if you're using Java, there's no way to get out of garbage collection. So that's kind of why I'm proposing this gradual approach where garbage collection is optional.
Mm-hmm. Yeah, it's very interesting. I was just going to jump over to Dominic actually. Let's take. Thank you, Michael. You mentioned RustViz, and I was thinking about Dominic's presentation and this visualization and how this could help users. But let's take Jürgen's question first. So you can say it if you want, Jürgen, if you want to jump in.
Sure. I just saw that Dominic, you have like a full VS Code plugin also out there, and I was wondering if you have observed how people use these asynchronous call graphs to debug problems. Have you talked to people? Have you observed people using it?
Yeah, the answer is no. I'm a tool developer at heart, so basically I produce the thing. I make sure it runs on real-world examples, and it satisfies my own needs as a developer. I've been programming for 20+ years. So this is my user study, not very, researcher-like. I love to do user studies, just didn't have the time yet. That's really the answer to that. I'm looking forward to doing a host of that in the near future. I've also talked to bootcamp providers who, of course, at the beginner level, they're always interested much more so than professionals in better tools that help you read code, understand code, because professionals already got it all figured out, right? So they are not as easily convinced. But definitely talk to people, and there's some things coming up in the near future, I hope.
Cool. Just as a quick addendum, I shot you an email before. I don't know if you saw it. We're running like a 300+ people course on web engineering, and I think the students will really enjoy this kind of tooling.
Yeah, I think so too. I actually, one thing that I did is I asked people, I think I did a talk a few weeks ago, and I did a survey. And one of the questions I asked is, do you think that this kind of tool would make programming, would make it easier to program? And it was mostly yes. And then would this kind of tool make programming more fun? And it was entirely yes. Even those who said that it would not necessarily improve my efficiency, they said it would make programming more fun because it makes it more interactive and you can just see things a lot. Absolutely great. Yeah, I saw your email. Definitely sounds very interesting. I'll reply to you right after the session. Awesome.
Thank you. It sounds like maybe potential collaboration. I wanted to also throw a question for you, Xing, or about your system and bidirectional programming, given that we're talking about users and how this tool could be received here that Dominic presented. Have you, in your case, tried out the tool with users, and how did they receive it, if you have?
Do you mean that we test our tool with students? Sorry,
Students or other people? Yes.
Because now our tool can only be used for functional languages, and the HTML webs written using our languages can be maybe difficult for most developers, and I think we plan to test our tool with user study, but it's just a future plan, I think. And we need to carefully design some practical examples and try to test whether the tool makes the development more efficient. Okay.
Thank you. I was just curious whether you saw any immediate sort of challenges in for instance, if the program the system that you're working with, if it grows beyond like one file, or I mean, do you have any issues around that? And I mean, you're in this stage where you haven't tried it with people yet and so on, but do you see if there's any like immediate challenges in making it into kind of more of a practical tool?
Sorry, can you repeat your question? And sorry, my listening is so poor to understand.
I always speak very quickly as well. Sorry. No, I mean, I was wondering, I saw your, in the paper and in your presentation, you have this screenshot of your tool and you see these sort of annotations that you use for the holes and so on. So if it grows to a project with several files and so on, do you see is it challenging, or does size kind of introduce issues or things in that direction? Have you thought about that, or do you have any sort of ways to deal with that?
I think our tool can be easily extend to write more longer program or write complex application, but now our tool is only it is only